Evaluate rational functions. We're going to start just by reviewing that difference between expression, equation, and function again. So a reminder that a function is a relationship between variables, and all that means is that a radical function is a relationship that's defined by a radical. So let's begin actually just by talking or looking at an example of what an expression looks like. So this would be a very typical radical expression. 2 times the square root of x plus 3. It's an expression with a radical. It's not equal to anything. X does not have a value. It's just a statement. A radical equation, we could start with the same thing, but then all of a sudden we have something that it's equal to, like that. That would be an example of a radical equation. Now we have an equation where there's a relationship between or I should say there's a relationship here, and there should hopefully be one value of x that makes this equation true. But as we've seen, some radical equations don't actually have solutions. And finally, a radical function is a function which has a value that depends on some radical. So a radical function might look like f of x equals this radical with x in it, or we might write f of x as y instead. That would be another way you could see it. But it's a function where the relationship between the value of the function, f or y, depends on some radical of x. So for example, if we have this function f of x is equal to the square root of 2x minus 1, we can determine the value of this function at x equals 5. So 5 has replaced x in the bracket, so that means that x equals 5. So what would that look like? Well, what it means is that in our expression where we had x, we now instead have 5. So it's 2, instead of 2 times x minus 1, it's 2 times 5 minus 1, and then all square rooted. So this would be the square root of 10 minus 1, which is also the same as the square root of 9, which is 3. So the value of the function f of x at x equals 5 is 3. We could also call this the y value. Let's determine the value of f of negative 2. So same thing, we're just replacing x in the function with the value of negative 2. Except this time, we have the square root of negative 2, or 2 times negative 2 is negative 4 minus 1, which is the square root of negative 5. Which means it does not exist. Reminder, if you have forgotten what those 3 letters stand for, does not exist. So the function actually doesn't exist at x equals negative 2. One way of thinking about this is that x equals negative 2 is outside of the domain of the function. And lastly, find x when f of x equals 9. So this is sort of the opposite way that this question can be asked, which is before we're asked, find the value of the function for a given x value. Now we're saying, what x value makes the function equal to 9? So to do that, we're now told the y value, so we know that 9 is equal to the square root of 2x minus 1 somewhere for some x value, and we have to find that x value. And how are we going to do that? Well, we're going to start by squaring both sides of the equation and solving this radical equation exactly as we were doing this previously. So 81 equals, when you square root, it goes away. So 2x minus 1. Then we add 1 to each side. And then we divide each side by 2. And we get that x equals 82 over 2, which would be 41. Now there's one last thing to do in that part C that we have to do, which is check our answer, x equals 41. We have to check it in the equation because it's very possible that we just solved an equation that doesn't have a solution, because that can happen in radical functions as we've seen before. So we have to check in that original equation that we just solved, which was that the y value is 9 and that we didn't know what x was. So 9 is equal to 2x minus 1. We need to check if x equals 41 is in fact a solution. So we're just going to go ahead, plug it in there. So 2 times 41 minus 1. So that would be 9 is equal to the square root of 82 minus 1. 9 is equal to the square root of 81. And is that true? And it is. So good, our solution is valid. Always check that though. And I just want to show you one last example where instead of having a square root radical, we have a cubed root radical. So in this function, g of x, we have the cubed root of x minus 6, and we're going to start by finding g of 14. So we have the cubed root of, and we replace x with 14, so we have 14 minus 6. Cubed root of 14 minus 6, so that would be the cubed root of, quick little bit of mental math, that'd be the cubed root of 8. And luckily, 8 has a perfect cube, or 8 is a perfect cube, I should say. 2 times 2 times 2 equals 8, so the cubed root of 8 is 2. Now, this could be that we could have a question where the result was not a perfect cube, and so you would just have to write your answer in simplest radical form. But in this case, we were able to take the perfect cube of that value. If g equals -2, let's go ahead and substitute -2 in there. So we have -2 minus 6, and now we have the cubed root of -8. In the previous question, we saw that negative and our alarm bells went off, but in this question, we actually have to recognize that we can take the cubed root of a negative number, because as you'll recall, -2 times -2 times -2 is equal to -8. So negative numbers actually do have cubed roots. They don't have square roots, but they do have cubed roots, and the cubed root of -8 is -2. So the negative values of x are in the domain of the cubed root function. And lastly, let's find g of x, or x when g of x equals -1. So that means that we know -1 is equal to the cubed root of x minus 6. So we know the value of the function, or the y value. Let's find the x value. So we'll have to start by cubing each side to get the cubed root away. Cubed root of or I should say -1 cubed is still -1. And then on the right hand side we have x minus 6, and then we just add 6 to each side, and we're left with x is equal to +5. So we can answer these questions for square root functions, cubed root functions, and any other root, but the most common ones you're going to see are square roots and maybe occasionally cubed roots as well.